Because we're doing the partial fraction to
not partial fraction.
Partial
derivative. Yep.
Of x.
Oh, of x. Correct. So we're looking for this, right?
So y isn't changing.
So y is not changing. Exactly. So is there theoretically is there something in there?
Yes.
Yeah. What is it?
Constant.
Big fat. It's a constant, so it comes out to 0. So it's not written in. Oh yeah.
From both sides.
So what are we trying to show? It gives you. I mean, I like these questions that are show this is true because you have a target. What are you trying to show that this is equal to? Trying to show it's equal to negative partial f partial x over f dz. So what are we trying to isolate here? We're trying to isolate this one, right?
Yeah.
So does it work?
Yeah.
Yeah, because so first of all, what do we know this is equal to?
1.
That's just 1, right? So does it actually come out? Sure.
Yes.
dz dx is equal to, you have negative partial f partial x, but then what's out front of this thing still? You still have this, right?
Yeah.
So therefore, does it work?
Yeah.
Yeah, you end up with not d.
Yeah. No, where does that come from?
It comes out because of this. Like, for example, I'll show you why. Because before you learn the chain, do you learn the chain rule first when you do differentiation? No, usually it's the power rule, right? You're like, oh, wow, f of x is equal to x squared, right? So what does f prime of x equal? 2x. There's actually something invisible right here. Do you know what it is?
dx.
There's an invisible dx right here. Because you're doing the chain rule, but what is the derivative of x? dx. 1. It's 1, right? So you've been doing that. Every time you differentiate, does the chain rule come into effect? Yes. But many times, what does it pump out? 1. So you don't write the 1 down. Over here, this is just like, for consistency's sake, what are you pumping out when you implicitly differentiate? Like, yes, you do not have to write. Like, for example, we didn't write there's a 0 here because when you differentiate y, which is a constant, what does it come out to be? 0. So we don't write it in. So yes, there's a threshold for completeness, right? It's kind of like when we prove something in calculus that relies on trig. Well, we're not, when we make a proof, there's only a certain threshold for how far you go back. Do you understand what I mean by that? Like, when you prove something in calculus, you might use trig, something that is just taken as truth in trig. And, for example, when we use the law of cosines in a proof for something down the road, do you also have to prove the law of cosines every time you use it? No, you don't. Although, we're talking about, like, the disassembly of math all the way back to, like, addition. No, you don't have to do that. So, does this make sense so far, what we've done? This is it doesn't make sense? Do you understand the algebra so far of what I've done in the last, like, 2 lines at least?
Yeah, I understand how you went from the thing above to the thing below.
Okay, so my guess is you're talking about this right here?
Yeah.
Can someone give another try as to where that comes from? When you implicitly differentiate, what are you doing? Go ahead.
First hold y constant.
You hold y constant, because why are we holding y constant?
It's a partial derivative.
With respect to x, right? So what are the only, so yes, there are 3 things here, right? But there are only how many inputs? 2. There's only 2 inputs, right? So when you're doing your implicit differentiation, you have to differentiate with respect to x of the x over y and this, correct?
It's inevitable that df dz is negative.
Well, hold on, ready? I'm not asking for an analysis right now. Stop. No extrapolation right now. But we're trying to understand this statement right here. Go ahead, Tori.
So c wasn't defined.
F all the way to x. So if we go from f to x, we have our direct connection, right? So which term is that? That's the first one, right?
Yeah.
Are you with me so far? So what's another way you can get to x? You go to z and then you go to x. Those are the 2 paths to get to x, right? So when you go from f to z, it's going to be partial f with respect to z and partial z with respect to x. That's literally what we have right there.
And there's a direct path from x to x, which is why there isn't like a dx.
Correct.
Okay.
There's a direct 1. It comes out. Yeah, anytime there's a direct path, yeah, you could eject a 1. Does that kind of vaguely help a little bit? Okay, well, I can teach.
Just go on.
Okay, got it. Okay. But this is visually pretty intimidating, but it's actually not that deep. There are second-order partial derivatives. What we're talking about are second derivatives in multivariable land. The key thing you have to realize here, the key thing is just the notation and what each of these means. So if you have a function in terms of x and y, you can take the partial with respect to x, or you can take the partial with respect to y, and then you have 2 choices. You could either then do the partial with respect to x, or the partial with respect to y. So any 2-input equation, any surface, is going to have 4 partials at any given point. The key thing by far at this point is understanding the notation. So usually, I mean, as is the case in most fields of math, if there's a way to write something without writing all of the pieces, mathematicians like to summarize. It just means you have to keep track of what order you're doing things in. So this is the key thing here. When you see f, x, y, that means the partial with respect to x, then with respect to y. So you see x, y, you go from the left to the right. Do the partial with respect to y, x, and then the partial with respect to y. Is it going to matter sometimes?
Yeah.
Yes. It's going to matter sometimes. Sometimes the end product is going to be the same. There's a symmetry property we're going to talk about, but you just need to know what this means. Theoretically, can this be extended for as many dimensions as you want?
Yeah.
Absolutely. You could have x, y, z, q, whatever, right? But you just go from left to right. You just go from left to right. Yes?
You do vectors.
I don't understand. Up here. So these are the same expression, and that's why you see that little like square thing. So this is the partial of z with respect to x, and then you take the partial with respect to y of what you get. So this and this are the same thing. That's just why you tend to see it written out. Like this is just the condensed notation. Does it have anything to do with squaring?
No.
No, not at all. You're not squaring a thing, right?
Well, I mean,
You're not squaring anything.
with respect to y. I mean, that's
Yeah. Yeah, just be careful. Anyway, I'm just explaining the notation.
In this one, which one is happening first?
This is happening first. You do this, and then you do this. Parenthesis rules still affect. You do what's inside the parenthesis.
How
This
would
is
you know on the other one?
on the other one. Well, look, you go from, and then what do? This is first. This is second. Yeah, I'm telling you. I'm just saying. It's not. Oh boy. Yeah, I mean, it's dangerous because you could start on the wrong path and end up in completely the wrong place. I understand. That's why we're emphasizing it right now. Yes, Brendan. What is fx going to be of xy?
y squared.
Y squared plus
6x.
e to the what? Y. And then you're just doing it again. And what do you end up with?
6e to the y.
6e to the y. So that's one of the second order partial derivatives for this. Find me the other three. Got a few of these here. So if I asked you for what's fyy going to be, who has that? What is it, Brendan?
It's going to be 2x plus 3x squared e to the y.
Who agrees? E to the y, right? Not ey. E to the y. Okay. We're good? You got your friends there? Okay. What about fxy? Who has that one? fxy. What'd you get?
I've got 2y.
Yep.
Plus 6x e to the y.
Who got that? Okay. Who's got fyx? Who's got fyx? What'd you get, Ray?
2y plus 6x e to the y.
Nice. Who agrees?
Same thing.
Ah, is it always? We'll get to that. We'll get to that. So these are our answers. I'm pretty sure we're pretty happy with these four. Next first, and then what do you do? Fy. So the first thing we need to find, if we're going to find this, we first need to find fx of 1, 2. And that's the rate of change with respect to x. So what stays the same? Y is constant. So if you do y is constant right here, where's 1, 2? There's the point you're at right there, correct? So if you keep y constant, you're looking at 2, that row. Is that correct? So if you're actually going to do this, fx of 1, 2 is going to equal approximately, again, this is approximately, you need some sort of quotient, correct? And it's going to be f of something minus f of 1, 2. That's how the book likes to do it, over 0. What? 1, depending on how far you go, right? It could be 2, because you could either go 6.48 to 9.6, or you could just go forward. Do you remember which? The book likes to just go forward, I think. Yeah, the book likes to go forward. It's easy. So they do what? 1.1, comma 2. So that's going to end up being approximately, was it 9.6?
No, 15.6.
9.6 minus, minus. No, f of 1.12 is 8, right? Over what? 0.1. So what is it approximately? It's about 16, right? So that's f of 1, 2. But now, what did we want? We wanted fx, but now we need to differentiate with respect to y. So how do we do that?
Find x constant.
What?
You hold x.
You hold x constant. You hold x constant, so those are going to be the columns, right?
And you find the derivative of them.
When you do this out, you end up with this. So this is approximately, it's going to be 12.88 minus 10.65 all over 0.1. So that's what? 22.3. So what have we found? Just to recap what we found. At at this point right here, at that instant, what is fx going to be equal to? 16, right? And what's fx right there? 22.3, right? So now they're asking for what's the rate of change with respect to y? So we fix x. What's the rate of change of these rates of change? It's the slope from,
Do it again.
it's right here. This right here is 22.3, and this is 16, and it's 0.2 because you're going from 2 to 2.2. That's the distance. That's the distance in y values. So you end up with, what do you end up with? 31.5, I think. If that's what you end up with? Yeah, you end up with 31.5. So the other half to this would be, we just figured out fxy. What could you also find out? They also asked for fyx. What do you think it's going to be if this is a nice function? It's going to be the same thing. If you compute it consistently, don't make a mistake, it should come out to be the same thing. It is very important that you can do both the numeric with a function and the numeric with a table. And just for consistency's sake, what does the book like to do? They like to take the point and go forward. They like to go up to the right. They like to go forward. They don't like to do the average.